experiment, and you can see the ruler moved. So right away you're like, what the fuck?
Yeah, the ruler moved only 2 millimeters. You didn't pay any attention, but I showed you, okay, the 0 point for the 1 mass 1 height. The rubber band is aligned with the 18.5 centimeter mark. Okay, and now for all the other cases, it's aligned with the 80.3 mark, because after I did this one, the 1 mass 1 height, I accidentally touched the ruler and it moved a bit, and it's only a difference of 2 millimeters. And I take into account that difference because, let's say for the 1 mass 1 height, let's say it went to the 16 centimeter mark, then I did 18.5 minus 16. And for all the other cases, let's say it also went to the 16 centimeter mark, I did 18.3 minus 16, so that gives you the real amount of stretch. I took into account the difference, and it's only 2 millimeters.
What do you do with the experiment for if the ruler is moving? So obviously you do have to move the ruler, okay, and obviously the numbers completely change, which means the numbers almost become the same number here in this case, because you move this ruler where the 14.8 happens, well, you move it, okay, in that direction, getting closer to the 13 point something.
No, it's 14.85, not 30 point something. Again, I took into account the 2 millimeter difference. So what I did was, I know what it was, 14.85. So I did 18.3 minus 14.85. Okay. And now you're here claiming that it should have been more than 1 centimeter to the left. No, draft. No, Gary.
So this is the 1 mass. Okay, I do it this way because my mouse doesn't always show up. For whatever reason, I gotta fix that, I guess. So this is the 1 mass going 2V. This is the 2 mass going 1V. Obviously, I would claim it's the same momentum. It's therefore the same capacity to do work. Blah 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 blah. Now he's getting a number 13.7 and 18.5, and instead of giving us just what the displacement number is, he gives us these stupid numbers, which are useless in this case.
Stupid numbers, right? Oh yeah, just showing the point where where the maximum stretch was, and then afterwards I showed you the subtractions. Oh, so stupid.
Because the ruler moved. So as you can see, the 17 mark is on the way out here over here, and it's way in here over here. So obviously way out.
Oh dear, you're taking the green line as a reference line. No, Gary, no. This is a reference line. I showed you. I placed the camera at the center over here, and you can see these are perfectly aligned. The rubber band was perfectly above the ruler. And again, I explained in the video that I moved the slow motion camera a little bit to the left, a little bit to the right, because I wanted to center the camera lens with the rubber band each time, such that the rubber band is in the middle of the screen. So once again, I showed you the video that the pendulum was aligned with, well, in this case, we have other numbers, but it was 80.3 and 80.5, okay? And the ruler is really close to the pendulum, so that remains the exact same place every time. That's the reference line. And then I started to move the camera to the left, to the right, to make sure that the maximum stretch is aligned with the camera lens, such that it's in the middle of the camera, of the screen. So there can be no parallax problem, okay? The 80.3 and the 80.5 remains at exactly the same position. And then I move to the left, and then you can see the exact place where the maximum stretch is happening. And then you simply subtract these numbers. God damn it.
Proportions are way off. Now the camera itself does okay-ish slow motion, but it's garbage lens. It's a whatever you call that, wide view, and it creates insane amount of parallax. That you don't even see it. See in this image.
So finally, I discovered how to get rid of the distortion of the slow motion camera. In the settings, there are 2 options. We have wide camera lens and normal lens. This is the wide camera lens, as you can see. The closer something is to the lens, the more it distorts, the more it bends. But if I change that to, so this is wide, and I can change that to standard. And now it's gone. It doesn't bend anymore. So how long did it take me to realize this? A couple of years. So gone. No more distortion. How's that? Finally. Let's do some experiments. This time, this camera will stay at exactly the same location for the entire experiment, for every single trial. All right. One mass, one height, trial 1. One mass, one height, trial 2. Mass, one height, trial 3. One mass, one height, trial 4. Height, one mass, 4 height, trial 1. One mass, 4 height, trial 2. One mass, 4 height, trial 3. Mass, 4 height, trial 4. Two mass, one height, trial 1. Two mass, one height, trial 2. Two mass, one height, trial 3. Two mass, one height, trial 4. Right, so now velocity check to see whether or not the one mass actually went twice as fast. So here we have the two mass. I took a print screen. Five frames later, I took another print screen just right before the collision with the rubber band. So here the bottom of the pendulum is aligned with 52.5. 5 frames later, it is aligned with the 50.3. That is a distance of 2.2 centimeters in 5 frames. Now for the one mass, let's see. It went faster, so unfortunately the bottom of the pendulum is a little bit more vague. So it's an area, actually. It's a wider area. But over here you can see kind of the pendulum through the middle here, and that is at 54.6-ish. 5 frames later, the center is around 50.4 or 5. And so 54.6 minus 50.5 is 4.1. Again, there might be some error. It could be 50.4 as well. So that would be 4.2-ish. So we have 4.2 or 4.1, and the other one was 2.2. When you divide these numbers, we have around 1.86, 1.9. So it's not a perfect 1-2 ratio. But again, there is some error due to this vagueness. But it's pretty close to twice as fast. Okay, here are the average results. The one mass going 1V produced an average stretch of 2.6 centimeters. The one mass going twice as fast, 5 centimeters. The two mass going half as fast, 3.63 centimeters. Now, conventional science as well as draft science predicts that when the one mass goes twice as fast, it should produce around twice as much stretch. So 5 divided by 2.6 equals 1.92. So this means that also for draft science, this experiment proves his model right. So this is a good experiment. However, the one mass going twice as fast, according to conventional science, this should produce around 1.41 times more stretch than the two mass going half as fast. So 5 divided by 3.63, that equals 1.37, which is a lot closer to 1.4 than to 1, which is draft science prediction. So that's a contradiction. For draft science, the fact that it produces twice as much stretch almost, that's good. That proves his model right. However, when we compare these, it's 1.37, so that's a garbage experiment. That's bad, it's flawed, it's cheated, it's crap, can't be true. That's strange, isn't it? This is good. The fact that it produces twice as much stretch, that's good. But this 1.37, no, bad. Now also, conventional science predicts when the one mass is doubled, so 1m 1v and 2m 1v, that ratio should also be 1.41. So 3.63 divided by 2.6 is 1.39, very close to 1.4. All the results are in line with the conventional science predictions. Kinetic energy is real. Deal with it. And you have been proven wrong with real physical evidence time and time again. Within all my latest collision experiments, whether it's vertically or horizontally, all the results always are in line with the predictions of kinetic energy. You never mention that. Why is it always the case that the results are always coincidentally in line with the kinetic energy results, predictions? Can you answer that? Nope, you're going to deny it. Face the truth. How long are you going to keep rejecting the truth?